Neutral Displacement Voltage YD angle measurement at lab. In this video, it is clearly explained about neutral displacement voltage in unearthed system. To understand neutral displacement voltage in unearthed system, this video explained about procedure to calculate neutral displacement voltage with the example and test procedure to confirm calculated value at lab. In YD1 YD11, neutral voltage is not available in delta side. So it is very difficult to understand phased neutral voltage in delta of the transformer. If you know that phased neutral voltage with reference to some angle, then you can confirm about the YD1 or YD11. To understand YD1 YD11 angles, test procedure to measure the angles is included in this video. In high impedance earth system, that is generator, transformer and unearthed system, transformer delta 3-wire system, virtual neutral is moved from normal virtual neutral point. Actually, in 3-wire system, there will not be neutral. So, 3-phase voltage only available, but 3-phase voltage is formed from neutral only. So, we are calling that neutral in 3-phase system virtual neutral. Virtual neutral is moved from normal virtual neutral point. This is called neutral displacement. Voltage between moved virtual neutral point and normal virtual neutral point is called neutral displacement voltage. Due to this neutral displacement from normal virtual neutral point, unbalanced load current or fault current will flow and damage transformer or generator. 13 degree. Another is Millman theorem. Millman theorem. Here you see three voltage sources are there. They are connected to the impedance Z1, Z2, Z3. Other side of the impedance are star connected and floating. The floating point is P. It is equal to V by Z1 plus V1 by Z1 plus V2 by Z2 plus V3 by Z3 whole divided by 1 by Z1 plus 1 by Z2 plus 1 by Z3. 1 by Rx is equal to 1 by Z1 plus 1 by Z2 plus 1 by Z3. I1 is equal to V1 minus Vx by Z1. I2 is equal to V2 minus Vx by Z2. I3 is equal to V3 minus Vx divided by Z3. In electrical, 4-wire system, 3-wire systems are available. 4-wire system, neutral wire will be there. That is R phase, Y phase, B phase and neutral wire will be there. IR plus IY plus IB is equal to IN, that is equal to 3 I0. That is summation of all current is equal to neutral current. 1/3 of the neutral is I0, 0 sequence current, or IN is equal to 3 times of I0, 3 times of 0 sequence current. VRN plus VON plus VBN equal to VN, that is equal to 3 B0. VRY plus EYB plus VBR equal to 0. That is phase-to-phase voltage sum equal to 0. 3-wire system, no neutral in it. That is R phase, Y phase, B phase voltage only available. IR plus IY plus IB equal to 0. That is 0 sequence current equal to 0. VRN plus VYN plus VBN equal to 0. That is 0 sequence voltage equal to 0. VRY plus VYB plus VBR equal to 0. Summation of phase-to-phase voltage equal to 0. We know VRY equal to VRN minus VYN. VYB equal to VYN minus VBN. VBR equal to VBN minus VBN. See figure 1. In this figure 1, R phase, Y phase, B phase are terminals. Z is load. One side of the load is connected to the source R phase, Y phase, B phase. Another phase, side of the impedance is connected as a star, and we are calling the point is N dash, that is virtual neutral points. In figure 1, 3-wire system, VRY equal to 110 angle 60, VYB equal to 110 angle minus 60, VBR equal to 110 angle 180, Z equal to 200 ohms, that is balanced load. Matrix of 1, 1, 1, 1 minus 1, 0, 0, 1 minus 1 into another matrix VRN dash, VYN dash, VBN dash equal to 0, VORY, VYB. This matrix equation coming from summation of all voltage equal to 0 and VRY and VYB. VRN another matrix VRN, VYN, VBN equal to matrix 1 1 1 1 minus 1 0 0 1 minus 1 inverse into 0 110 angle 60 110 angle minus 60. From that we can get the voltage VRN dash equal to 63.5 angle 30, VYN dash equal to 63.5 angle minus 90, VBN dash equal to 63.5 angle 150 volt. Now we are going to see matrix used to find out VRN, VYN, VBN from VRY, VYB, VBR voltage. We know VRY equal to VRN minus VYN, VYB equal to VYN minus VBN, VBR equal to VBN minus VRN. In three-wire system, VRN plus VYN plus VBN equal to 0. From this, the equations are 1 into VRN plus 1 into VYN plus 1 into VBN equal to 0, 1 into VRN minus 1 into VYN in plus 0 into VBN equal to VRY, 0 into VRN plus 1 into VYN minus 1 into VBN equal to VYB. From these equations, we can form the matrix 1 1 1 1 minus 1 0 0 1 minus 1 into VRN VYN VBN equal to 0 VRY VYB. That is VRN VYN VBN matrix equal to 1 1 1 1 minus 1 0 0 1 minus 1 inverse matrix and multiplied to 0 VRY and VYB. So VRN VYN VBN matrix equal to 1 by 3 2 by 3 1 by 3 1 by 3 minus 1 by 3 1 by 3 1 by 3 minus 1 by 3 minus 2 by 3 matrix into 0 VRY VYB. VRN equal to 2 by 3 into VRY plus 1 by 3 into VYB. VYN equal to minus 1 by 3 into VRY plus 1 by 3 into VYB. VBN equal to minus 1 by 3 into VRY plus 2 by 3 into VYB. For VRY equal to 110 angle 60, VYB equal to 110 minus 60, VBR equal to 110 angle 180 volt, we will get VRN dash equal to 63.5 angle 30, VYN equal to 63.5 angle minus 90, VBN dash equal to 63.5 angle 150. Virtual neutral of delta winding. You see the here, stall delta transformer is connected. That is, primary side is star, secondary side is delta. This delta is connected 3 resistors, load resistance, and made as a star point. Transformer voltage ratio equal to 1 is to root 3. 3 transformers, that is 240 bar 415, that is ratio is 1 is to root 3. All are resistance load, RL, are connected as one above. That is a star point of the RL connected as a N dash. RL equal to 200 ohms. N dash is virtual neutral of delta. If we apply voltage VRN equal to 63.5 angle 0, VON equal to 63.5 angle minus 120, VBN equal to 63.5 angle 120 volt, then VRY equal to 110 angle 60, that is YN phase reverse. VYB equal to 110 minus 60, that is VN phase reverse. VBR equal to 110 angle 180, that is RN phase reverse. VA1 N dash equal to 63.5 angle 30 volt. VB1 N dash equal to 63.5 angle minus 90. VC1 N dash equal to 63.5 angle 150. Neutral displacement voltage. See in the figure, one star delta transformer is connected. RL, which is forming the virtual neutral point of the delta. ZR, ZY, ZB are load resistors. This load resistor, one side is connected to the delta, another side is connected as a star. That point we are calling as a P. Transformer voltage ratio equal to 1 is to root 3. Three number transformers 240 bar 415 volt RL, ZR, ZY, ZB are connected YD11 as above. RL equal to 200 ohms. If we apply voltage VRN equal to 63.5 angle 0, VON equal to 63.5 angle minus 120, VBN equal to 63.5 angle 120 in primary side, then VA1 N dash equal to 63.5 angle 30, VB1 N dash equal to 63.5 angle minus 90, VC1 N dash equal to 63.5 angle 150. If ZR equal to 100 ohms, ZY equal to 200 ohms, ZB equal to 200 ohms, then neutral displacement voltage VPN dash equal to 15.88 angle 30 volt. Measured voltage across VP, P and N dash using voltmeter with phase angle with reference to VRN. VPN dash equal to 63.5 angle 30 divided by 100 plus 63.5 angle minus 90 divided by 200, 63.5 angle 150 divided by 200 whole divided by 1 by 100 plus 1 by 200 plus 1 by 200 equal to 15.88 angle 30 volt as per Millman law. Vx equal to V1 by Z1 plus V2 by Z2 plus V3 by Z3 whole divided by 1 by Z1 plus 1 by Z2 plus 1 by Z3. Lab test result. You see in the table, first is serial number, second is VRN dash, VON dash, VBN dash. ZR, ZY, ZB. This is load resistance. Theoretical VPN dash, that is neutral displacement voltage due to the load ZR, ZY, ZB. You measure the voltage and record in that one and find the error. This is VRN dash and VON dash, VBN dash are virtual neutral phase to neutral voltage. That is 63.5 angle 30, 63.5 angles minus 90, 63.5 angle 150. If suppose ZR is equal to 100, ZY is equal to 200, ZB is equal to 200, then theoretical VPN dash neutral displacement voltage equal to 15.88 angle 30. If ZR is equal to 200 ohms, ZY is equal to 100 ohms, ZB equal to 200 ohms, then neutral displacement voltage equal to 15.88 angle minus 90. If ZR is equal to 200 ohms, ZY is equal to 200 ohms, ZB is equal to 100 ohms, neutral displacement voltage equal to 15.88 angle 150 volt. We measure the actual VPN dash and find the error in that one. Note, the data in this example is used for calculation purpose only to understand the subject. Now we are seeing neutral displacement voltage of three-wire system. Due to different load, the start point of the load, that the neutral point, is displaced from virtual neutral point. That is, we are calling as a neutral displacement. Due to this one, what will happen? The load current will vary in each phases. Now we will see the load current variations due to different load. Current in ZR, ZY, ZB we have to find out now. VA1 N dash equal to 63.5 angle 30. VB1 N dash equal to 63.5 angle minus 90. VCN VC1 N dash equal to 63.5 angle 150. ZR is equal to 100 ohms. ZY equal to 200 ohms. ZB is equal to 200 ohms. That is, load resistance is varying. Neutral displacement voltage VPN dash equal to 15.88 angle 30 volt. Current in ZR, that is, R phase current due to the load variations. ZR current in ZR equal to 63.5 angle 30 minus 15.88 angle minus 30 whole divided by 300 equal to 0.47 angle 30. Current in ZY 63.5 angle minus 90 minus 15.88 angle 30 whole divided by 200 equal to 0.36 angle minus 101. ZB equal to current in ZB equal to 63.5 angle 150 minus 15.88 angle 30 whole divided by 200 equal to 0.36 angle 161 ampere. So due to the different load, the load current will vary. If the neutral displacement is not there, the current in each phase will be equal. If 400 ohms, 800 ohms, 400 ohms are connected across RY, YB, BR phases, what is the load current from delta winding? That is, delta is connected to the delta. How to find out the current? Procedure. Find star impedance from delta impedance and find load current. ZR is equal to, that is, star resistance equal to ZRY into ZBR whole divided by sigma ZYB. That is, first you convert that to delta resistance impedance to star impedance. That is very simple. So if you take ZRY, it is covered by ZR and ZY. So this is delta to star. Sigma will come in the denominator. Numerator, two impedance multiplication. Denominator, one impedance will be there. So ZR is equal to ZRY into ZBR whole divided by Z sigma ZYB. That is equal to 400 into 400 divided by 1600. That is equal to 100 ohms. Similarly, ZY, that is equal to 200 ohms. ZB equal to 200 ohms. So current in R phase equal to 0.47 angle 30. Current in Y phase equal to 0.36 angle minus 10.1 ampere. Current in ZB equal to 0.36 angle 161. YD11 confirmation. See the here. This is a star delta connected transformer. This is we are calling as a YD11. In delta, you don't have the neutral point. So we are creating a virtual neutral point and comparing that one. To get an idea about YD11, we have to do this test. See here, RL, three resistors star connected and form a neutral point, that is N dash. This neutral and primary neutral are isolated. If we short it, we can compare the angle between the primary and the secondary angle. Now see here, right side one transformation vector given here. VRN and VYN, VBN primary system. VRN, YVN, VBN is a secondary system. This VRN of the secondary is leading VRN of primary system. So we are calling this is YD11. Transformer voltage ratio is equal to 1 is to root 3. That is 240 bar 415 volt. Three transformers are connected as above. RL equal to 200 ohms to form the virtual neutral point. N dash is a virtual neutral point of delta. Apply voltage VRN 63.5 angle 0, VYN 63.5 angle minus 120, VBN equal to 63.5 angle 120. Measure voltage across A1 N dash, B1 N dash, C1 N dash using voltmeter with the phase angle with reference to VRN, that is H side RN voltage. It will be VA1 N dash equal to 63.5 angle 30, VB1 N dash equal to 63.5 angle minus 90 volt, VC1 N dash equal to 63.5 angle 150 volt. It confirms transformer is connected as YD1. That is, VRN voltage of LV side is leading VRN voltage of HV side. The same can be confirmed by voltage phasing out test. We already explained about voltage phasing out test in some other video. YD11 means VRN of LV is leading VRN of HV. Here we formed the virtual neutral and completed the test. But at site, we didn't connect RL and we want to form the virtual neutral point. So A1, that is LV side, A1 and N we shorted and apply voltage in HV side and measure the voltage between RN, R1, RY like that. That is separate test. YD1 confirmation. We are going to the test as in YD11 only. In YD1, VRN of LV side is lagging VRN of HV side by 30 degree. That we are going to confirm. Connect the transformer as shown in figure. RL is the load, is a virtual neutral forming resistor. Transformer voltage ratio 1 is to root 3, that is 240 bar 415 volt are connected used. Three transformers are connected as above. RL is equal to 200 ohms to form a virtual neutral point. N dash is the virtual neutral of delta. Apply voltage VRN equal to 63.5 angle 0, VON equal to 63.5 angle minus 120, VBN equal to 63.5 angle 120 volt. Measure voltage across A1 N dash, B1 N dash and C1 N dash using voltmeter with phase angle with reference to VRN. It will be VA1 N dash equal to 63.5 angle minus 30, VB1 N dash equal to 63.5 angle minus 150 volt, VC1 N dash equal to 63.5 angle 90. It confirms transformer is connected as YD1. The same can be confirmed by voltage phasing out test. We already explained about voltage phasing out test in some other video. At site, YD1 confirmation is done by connecting A1, that is R phase of LV, R phase of HE, and measure the voltage with less voltage applied in HE side. After that, they confirm it either it is YD1 or YD11. From this video, we understand about Millman theorem, virtual neutral of delta winding, forming the virtual neutral of the delta winding, neutral displacement voltage and current in three-wire system due to neutral displacement voltage. YD1, YD11 confirmations. Thank you very much for watching this video. If you need any clarification, you send mail to us. Our email ID is anbu.electric.y@gmail.com.